Hey everyone, Paul here for a video for our last assignment of this week. This assignment is about trying to really combine some of the ideas we learned in counting with these ideas of probability, okay? So here's the kinds of questions we're going to be looking at. You flip a coin 3 times. What is the probability you get a heads on the first flip, a tails on the second, and a heads on the third? Okay, let's think through this, right? So first thing, let's put this into our notation that we've been using. This is really just asking this, probability of heads, tails, heads. Now, we've been solving these kinds of questions by using this formula. The probability of some outcome occurring is the number of ways the outcome can occur divided by the total number of possible outcomes, okay? A very obvious way to solve this would be by using a tree diagram, which is it's a little bit of work, right? But it does work for us, okay? So here's our tree diagram, and here's all of our different possible outcomes. And in this case, the total number of possible outcomes would be 1, 2, 3, 4, 5, 6, 7, 8. We have 8 total possible outcomes. So probability of heads, tails, heads would be something over 8. And of all these outcomes, how many of them are heads, tails, heads? Well, 1. And that's it. This 1 is heads, tails, heads. And so that tells us that the probability of flipping a coin 3 times and getting heads in the first one, tails in the second, heads in the third one is 1 over 8. Now I want to point out, please, please, please note that heads, heads, tails and heads, tails, heads are not the same thing, even though they both have 2 heads and 1 tails. Because in this problem, in this scenario, the order that you're getting the flips matters. So this is not saying just getting 2 heads and a tail. It's saying a heads in the first flip, a tails in the second, and a heads in the third. It's only this outcome. But I hear what you're saying, Paul, I don't want to make a tree diagram every time. I don't blame you. I don't want to make a tree diagram every time either, right? It's a lot of work. So let's think about this problem with the fundamental counting principle, right? Which tells us that if we have different things, different events that we're doing, right, we can multiply the outcomes for those events to get the total number of possible outcomes, okay? So here's how we would think about this. In this scenario, how many events are there and how many outcomes are there? Well, 3 flips of a coin. So there's 3 events. Each event's the same thing. It's flipping a coin. And each event is the same event. It has the same number of outcomes. It's 2, right? So we saw this idea of like this blanks method where we can take the 3 events and they become 3 kind of separate blanks, right? So there's our 3 blanks. And then the number of outcomes goes in those blanks, 2, 2, 2. And we multiply them, right? We are multiplying these because it's the fundamental counting principle says we multiply the number of outcomes to the total. So 2 times 2 times 2 is 8. That's this 8 that we got right here. But what about this 1? Well, this part, this 2 times 2 times 2 is the denominator. And the numerator is basically the same thing. It also has 3 blanks. And in the numerator, we're asking ourselves, how many ways can we get the outcome that we're looking for? So if you flip a coin, how many ways can you get heads? Because we're trying to find the probability of getting heads first. Well, a coin has 1 head, so that would be 1. And how many ways can you get tails? Well, there's 1 tail, so that's also 1. And lastly, heads, and that's another 1. And we also multiply those. And 1 times 1 times 1 equals 1, and 2 times 2 times 2 equals 8. And there's that same value of 1/8, but we didn't have to make a tree diagram and physically count the things. We can use the fundamental counting principle, right? So notice we use the fundamental counting principle in both the numerator and the denominator. The numerators happen to be all 1s, but we still used it there. We had 3 blanks in the numerator, 3 blanks in the denominator. This was the total number of outcomes, and this was the number of ways that we can satisfy the condition of getting a heads, okay? Let's go at 2 more examples, right? Here's some silly game we made up where you spin a spinning and you roll a die, right? So here, right, let's think about events and outcomes. Events, well, this has two events. It has the spinner event and it has the die event. And for outcomes, how many outcomes are there for the spinner? Well, there's 4 sides, so there should be 4 outcomes. And there's 6 sides in a die, so there's 6 outcomes for the die, right? So if we want to find the probability of getting red on the spinner and a 1 on the die, we can do the exact same thing we just did, right? So we're going to take our 2 events and we're going to make 2 blanks. We're going to make them in the bottom part, the denominator, and in the top part, okay? Now, our total number of outcomes for the spinner is 4. And how many ways can you get red on the spinner? Well, the spinner has 4 equal sections, and one of them is red, so that would be 1. And on a die, how many ways can you get a 1 on this 6-sided die? Well, there's 1 way, and there's 6 total sides, so that would be 1 and 6. And the fundamental counting principle says we multiply these values, giving us 1 over 24, which is about 4%. Pretty small, pretty unlikely for that to happen, right? Notice how we did this. We didn't make a tree diagram. We didn't count that way. We counted using the fundamental counting principle. Now, this works even for numerators that aren't all ones and ones. Let's look at this last one. Probability, this is a weird question, of getting a red or blue on the spinner and a 3 on the die. Okay, so we still have our 2 events. Right, make sure you can see that. And we know that the spinner has 4 total outcomes. How many of those outcomes are red or blue? Well, there's 1 red, there's 1 blue, and so that would be 2. Right? There's 2 possible outcomes that satisfy red or blue. And what about the and 3? Well, the die has 1, 3, and the die has 6 total sides. And now we just use the fundamental counting principle and multiply. And we get 2 over 24. That's the probability of getting red or blue and a 3. Now, just to take this one step further, we're not going to ask you questions that are this hard, but just to show you how we're using the fundamental counting principle, right? Let's come up with a crazy one, right? Let's have the probability of not red and even. How do we do not red and even? It's the same thing, right? We're going to still use the fundamental counting principle. We're going to have our 2 events, which are the spinning of the spinner, the rolling of the die, and we're just counting the number of total ways, which was 4 and 6. And then, how many ways can you get not red? Well, there's 1, 2, 3 not reds, so that would be 3. And how many ways can you get even on a die? Well, there's 1, 2, 3 even numbers. So that would be a 3. And we multiply. 9 over 24. And that's the probability, right? It's somewhere around like 40%, about that. That's the probability that you would get a not red color and an even number if you played this game, right? We're just using the fundamental counting principle, which says that you count the number, you have the number of events as these blanks, and you put the number of outcomes either that satisfy your condition or that are the total, and you just multiply. It's pretty straightforward. I hope that's okay. I get that these videos are sometimes hard to process, and if it's confusing, I'm sorry. I'm probably not doing the best job of explaining it, right? So please come to class, come to office hours, ask us questions. We're here to help. We love you guys. We miss you. We hope everyone's doing well, and we will hopefully see you soon. Bye-bye.